Okay, so we're dealing with situations where we want to find the highest common factor of two integers, and then we want to find the coefficients that satisfy Bézout's lemma for those integers. So we want to find, for a and b, the highest common factor of a and b, and then we want to find x and y in the integers such that the highest common factor equals ax plus by. So here's an example where a is 51 and b is 42. Using the standard Euclidean algorithm, we find the quotient remainder after of a divided by b. We find the quotient remainder of a divided by b, and then the HCF of a and b is equal to the HCF of b with the remainder of a divided by b. Repeat this process, and we find that the highest common factor is 3. Then they make the remainders as subjects, and we can do some manipulation and find x and y, which satisfy Bézout's lemma here. Now there's a nice computational algorithm, which is this one, detailed here, which you can do with pen and paper quite nicely. So I'll explain that now. So same problem, but without all this algebra that we showed before. So essentially what you do is you put your a and b to start with in one column, and what we'll be doing, so we'll start with 51 and 42 beneath it, and this column here will be our quotient, will be our a's and b's, and so the next step we'll be working with this and the remainder of 51 divided by 42. We'll write down the quotients in a little column to the left, and then here we'll be working with a matrix of temporary variables, 2 on the top, 2 on the bottom, and on each iteration we'll be working with the 2 on the bottom from before, those will now be at the top, and the 2 on the bottom will be generated from the quotient and the remainder and the current working values as seen here. The values here are the lambda values you see on the screen described here. So for this current a and b, we'll have lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2. But those are just details. What you really need to know is you just write down your first a, your a and your b here, and then we start with what is essentially the identity matrix, 1, 0, 0, 1. On each step, we will then write down the quotient of 51 divided by 42 in this case, which is just 1. 42 only goes into 51 once, so we'll put down a little 1 here. And then our new values will be our upper value minus the quotient times the lower value, and the same for this column, the upper value minus the quotient times the lower value. So this field will be this minus this times this, and this field will be this minus this times this. So this is 1 minus 1 times 0, which is just 1, and this will be 0 minus 1 times 1, which is negative 1. The field here will be the remainder of 51 divided by 42. So 42 only goes into 51 once, so the remainder is 51 minus 42, which is 9. And just repeat. So 9 goes into 42, 9, 18, 27, 36. The next would be 45, so it only goes in 4 times. Quotient is 4. The remainder is 42 minus 36, which is 6. And then this will be this minus this times this, which is 0, minus 4 times 1, which is negative 4. And this will be this minus this times this, 1 minus 4 times negative 1, 1 plus 4 is 5. And just keep repeating. 6 goes into 9 once, with remainder 3. This is 1 minus 1 times negative 4. 1 plus 4 is 5. And this will be negative 1 minus 1 times 5, which is negative 1 minus 5, which is negative 6. 3 goes into 6 twice, with remainder 0. And now that we've hit a 0 here, these are our final values. This is the highest common factor. This is the coefficient for our a value, and this is the coefficient for our b value. So the HCF3 equals 5 times 51 minus 6 times 42.